Thanks for the introduction. I'm Ted, and a little bit more introduce about myself. So I enjoy building practical systems, especially those systems which are backed by fundamental theories. So my major works include hotstop protocol and its node protocol family, or call it Avalanche. So hotstop protocol is the main consensus protocol used by Facebook LibreObject. And also, as a research effort, I implemented the libhotstuff, which already surpasses the state-of-the-art PBFT implementation performance. So this talk will be mainly about my main work at Cornell and Alva Labs, which is the Avalanche protocol. So what does the title mean? What does the infrastructure for blockchain 3.0 actually mean? So what is the infrastructure? So how is it like in the year of 2019? To answer this question is kind of hard, right? So let's try to put together all the key ingredients that already exist in many main chains or cryptocurrency startups. So if we manage to put together all fancy technologies, consensus protocols, and designs, architecture together, what can we get? We can get some giant beast, right? It's a really complicated, system architecture. But isn't that really complicated? If you look from the left-hand side, you have the users or user agents like web browsers. They just use their apps to access some, third-party service provider like exchange or digital wallets. And those exchange and the digital wallets in turn access the main network like the miners or the full nodes inside of some consensus algorithm. And of course, the system could be sharded because sharding has become the most popular term in this area for a while. So let's imagine an extreme system which has like two heterogeneous chains at the same time. So we have our good old school ledger, which is a linearized log, but we also have some fancy DAG-like thing. So it looks like this graph is very comprehensive because it includes everything that you would like in your infrastructure, right? So what about 3.0? There has to be 1.0 and 2.0, right? Well, let's take a look at it. So 1.0, Nakamoto area, I think there's no dispute if we name it as 1.0. And it's just like a chain or a tree of proof of works that are actually contained in the blocks one after another. So the longest chain contains the most of the work, and that will be chosen as the so-called canonical chain. So what's the problem? First of all, let's talk about its benefits. So proof of work is a good thing if you think about it as a SIBO prevention because it automatically addresses the problem. So you don't have to have extra, argument about it. It's like, extra feature while you are using it as a consensus. And also, the old school blockchain has very graceful safety degradation. It means you can choose the number of blocks you wait until a transaction is confirmed. And you can also based on the number of possible potential Byzantine adversaries in your system to choose your own parameters. So you have to have your smooth knob, which you can tune. And it also has loose membership knowledge. So it doesn't have to assume like everyone knows everyone else, unlike many other proof-of-stake protocols. The downside is obvious. As all we know, proof of work wastes a lot of energy and is very slow, both in terms of throughput and latency. And it also has poor efficiency and safety. What does that mean? So that's a cool thing if you think about it, because for other solutions, such as PBFT-based solutions, they are usually fast. So and they usually have deterministic safety, so it's always safe. But they require some hard limit on the Byzantine adversaries. So you cannot support more than 1/3 of the network misbehaving. Whereas in blockchain 1.0, you have like a smooth breakdown point, so you can choose your parameter. And also, so why is it inefficient in 1.0? This is because assuming there is 1/3 of your system is misbehaving, then in blockchain, if you still use the 6-block rule, then guess what your safety guarantee is? It is not like 99.999%. It's just 90%. You have 1 out of 10 chance of double spending the money. So which means the 2.0, of course, It's more reliable in terms of that, but the problem is it doesn't scale that easily. So it usually has a leader which optimizes the performance, so everyone knows what to to write on the ledger. And there have been other randomized BFD approaches which use different models, but usually in that case, you have several proposals competing each other, and the situation could be made worse if you have more nodes. So the quorum-based solution isn't that good, and also it's complicated. Here's a picture taken from an article in an academic magazine, Login, and apparently the author was very disappointed about, already in 2013 that this line of research is overly complicated. This is called the saddest moment. So this complication also implies it's very hard to optimize the scalability for this, traditional quorum-based solutions. So it looks like we have our definition for 1.0 and 2.0. So according to the definition, it sounds to me more like, consensus 1.0 or 2.0. And that actually is, because, consensus protocol, as I previously shown in the first slide, the giant beast, it sits in the middle between the user and the ledger or the smart contracts. So it provides a way to magically serialize or linearize all operations or somehow confirm their operations in a decentralized way. It is what makes it possible to have decentralization. So, but wait, and I think before I talk about 3.0, and many of you will ask, we do have shardings. What are you talking about? You don't have to find better protocols. But sadly speaking, sharding is a different thing. So sharding, first of all, does not address the scalability issue of the consensus itself. It comes as a cost of trading off between the fault tolerance, so the level of tolerance of failures in your system, and the performance. So it's making the trade-off, not actually improving the thing overall. This is like the case where you have a badly made soup. So then somebody just comes to you and say, let's try sharding. You can add more gochujang to your soup, so it tastes better, right? But sadly, no matter how much gochujang you actually add to your bad soup, it's still a bad soup. It tastes bad in the first place. So why couldn't we just make budae-jjigae from the very beginning? And that's very spicy, and that's delicious. And budae-jjigae also comes with gochujang in it, right? It's part of the ingredients. So can we do that? Is that possible? Yes, it is. So there's a paper about a new kind of paradigm that could be used for probabilistic safety consensus, which is called the Snow family or avalanche. And the paper was out in 2018. And it's very different from previous approaches, such as quorum-based solution and Nakamoto consensus. So this is inspired by epidemic protocols and gossip networks. It actually introduces new methodologies that combines the best of, or some of the best from the previous two generations. So it's graceful in safety degradation. It has loose membership knowledge. It is very fast regardless of network size. And I'll show that later. And it's energy efficient. It doesn't require proof of work. And also, I'll show you in a second in a demo that the operational logic just makes sense. So although the analysis is really, really difficult, you should ask our other co-founder about the math behind it. And he should write a book about it. So but wait, and many of you can ask again, why do we want another protocol that claims very high TPS? So what's the point of that? So I think it's an unfortunate thing that people are nowadays too obsessed about pursuing the single word TPS. Because throughput, TPS reflects the throughput. Throughput only reflects how much load the system can buffer, while latency, another metric, reflects how fast a single user can be served. That's the thing that matters the most to the users, right? So we need them both for our evaluation. Let's take daily life as something in daily life as an example. So assume we have a bank branch that can serve a single person that very quickly. very low latency latency, not enough throughput. I mean, what if there are too many people for them to serve? So we had to consider throughput. But is TPS alone good enough? Let's imagine that extreme case where, I want to do a crypto startup. I just, hire a bunch of trucks which carries a lot of hard drive like Samsung, SSDs, and it can transport petabytes or exabytes of data, from one place like Icheon to Seoul in just, 1 hour or so. And that's very high throughput if you think about it. It's much more than, giga transactions per second. But what's the point of that? The latency is very, very high. So talking about throughput without latency is also meaningless. So what about Avalanche? So for Avalanche, let's first look at the throughput. OK, throughput, thousands of transactions, and scalability. You can notice the x-axis is the number of nodes, and each time it gets doubled. So it's a log-scaled x-axis. We're putting very high standards to ourselves. So also, the y-axis reflects the number of transactions confirmed in the whole system at a time. As you can see, is the degradation. So you can barely see any degradation in the graph. And what about latency? And don't forget about our previous argument. The latency, if we aggregate all transactions in the experiment where there are 2,000 nodes in the previous diagram, the last 2 bars, and plot them in this form, like a histogram, to accumulate how many transactions are confirmed within certain time window, then what we notice is most of the transactions are finished from 0.1 second to 0.4, and the average time is just 0.2 seconds. Let's try a more realistic setting. So let's put 2,000 nodes all participating in consensus in 20 cities across the world. So all nodes directly do consensus. And what's the result here? So the result is still very promising. If you look at that, 3,000 TPS, OK, decent. And as for the latency, you will see similar histogram, but of course, a little bit higher absolute latency, but still very good for a consensus protocol like this. So that's very interesting. So tell me how this protocol works and why is it so efficient. This protocol works by gossip. So gossip network is not only a way to deliver data, but can also be used as part of the consensus. So imagine there are n people discussing whether some rumor is true. So 2 states, like whether true or false. And everyone just independently choose k other people at random, so they sample the crowd. For example, there's Alice in the crowd, ask those k people whether the rumor is true, which is a query. And she updates her current confidence, because she may now currently have a bias. And instead of sampling all participants, what makes this protocol very different from previous approaches is you only sample k out of n, where k is a very small constant. So in this picture, Alice is sampling 5 others, and the results are 2 yellow, 3 blue. So the majority is blue, which goes against Alice's current bias. While at the same time, Bob also does similar sampling. So probably he gets a yellow. So then, if they are not so convicted to their current state, they may flip their states because, I'm hearing more blue from the community, so I assume it's blue, or assume the rumor is true. Whereas if I hear more yellow from the community, I think, well, the rumor doesn't exist. It's fake. And we do have a demo about this whole process, and it's very beautiful. So I need a little bit help here to access the link. And let's just wait for a few seconds, I think. Thank you. So let's just click the run button and see how the system works. So it looks like the system was originally chaotic, but due to some slight fluctuation in the system, the final state of the system will quickly collapse to one side of the color. So let's try it again. Probably this time we'll get a yellow, but it could still be blue. Who knows? OK, So this time we're getting yellow. Yeah, thanks. So shall we move back to the next slide? Thank you. So it looks like this protocol requires a magical K, which is a small sample of the network. And to be honest, the realistic choice of K is actually really small. It's just like around 10 to 20 for any practical size of the network. So it's not that affected. And this protocol doesn't require any proof of work. So this is all great. But we haven't talked about the infrastructure yet. And I'm always running out of time, right? That's deliberate, because remember that giant beast? That's not imaginary. That's actually our architecture, the thing that we plan to build. So we want to utilize the nature of pure payments, because they don't have to be linearly ordered, so they can reside on the DAG, which can be much, much faster than trying to put together a linear log. So we have our avalanche part, but we also want to support DApps, and also I'll explain why it is called platform of platforms. That's why we have Snowman, which is a conventionally linearized ledger. So if we zoom into Snowman, we'll notice that it is possible to create your own chain, just like you're using ERC20 to do your own token, which is kind of cool if you think about it. So, because people used to debate about whether you should use EVM or use WASM, you should use this versus that, this coin versus that coin. But shouldn't we just use them all? Or isn't that good if we have a virtual machine that's for the virtual machine, right? So that way you can deploy your own Ethereum full functionality chain at the cost of smart contracts. And that's a cool idea. That's why we call it platform of platforms. And as I told you, sharding is just another trick, because if you notice this, if you look at this, you already notice that we have different colors, which means your own chain could be sharded, right? It doesn't have to be fully replicated across the entire network. So that way, we're making our own delicious budae and with gochujang at the same time. Thank you. 감사합니다.
Thank you very much. So now let us have the time to answer some questions from the audience. 테디님께 들어온 질문 중 몇 가지 소개해 드리도록 하겠습니다. 첫 번째 질문입니다. The first question is, when Bitcoin is representing blockchain 1.0 and Ethereum is representing blockchain 2.0, then which coin is representing Bitcoin 3.0?
Oh, so I think the 1.0, 2.0 things are just defined for the purpose, for the presentation. Everyone can have their own definition of those version numbers. But to answer the question, I think because so far both Bitcoin and Ethereum use the 1.0 technology I mentioned, no offense, we are using different numbering here. And they might be 2.0 because they have like smart contracts. For example, in this case, probably we should have numbered it as like 1.0, 2.0, 3.0, 4.0, and we're 4.0. So it's just a matter of numbering. But Ethereum at its core still uses the Nakamoto consensus. So I think that's what we are different from them, because we're not using proof of work at all.
Okay.
Yeah.
Thank you. And 다음 질문입니다. Next question is, which features will be strengthened or complemented in Bitcoin 4.0?
First to correct, it's not Bitcoin. And so strengthened or weakened. So what we hope is, as for the payment part, we are very confident that we are not losing anything here, because we are just trying to solve the problem. Like, we're making the budae. We are not trying to make a bad soup taste better. So that way, we're not just adding ingredients to it. We're just remaking the whole meal. So that's what we are strengthening. So then what parts could we actually weaken? So far, I cannot think of any. If if you have a good idea, please feel free to point out the problem or actually there are challenges. For example, if you want to do smart contract, you still want a fully replicated linearized log. And of course, theoretically speaking, this linearized effort has to be more expensive than just keeping track of a DAG. I think in that sense, it's just like if we compare our snowman to our avalanche, both are inside of Ava system, then probably snowman will have slower performance compared to avalanche. But I think in that sense, it is still much better than like previous generations when it comes to scalability. It's like a self-comparison for sure. Yeah, if you only do payment transactions, then you can have very fast speed. This is because the DAG solution is faster than before. So hope this answers the question.
Okay. 다음 질문입니다. There are already many so-called blockchain 3.0 networks like Algorand. It seems like the question is not only a matter of technical advancement, but of adoption by developers, which is arguably harder. How does Ava Labs seek to solve this issue, maybe?
Oh, that's a great question. So we are all also well aware of this problem. So we know that there's a huge gap between the theory and the system, and another huge gap between the system and the final business part. So the way we try to first break through or build a bridge across these gaps is the first thing is very simple, like open source the code in the end and let everyone run the system. And that sounds like a very trivial, simple goal. Like, why would this speaker talk about this? But if you think about every single coin you previously know, are you able to download the code? Are you able to run it? Are you able to easily join the mainnet as you would in Ethereum? Probably not, right? If you really want to renovate the space, you first have to make sure your product is usable and it works out of the box, not just played by those very few investors or super nodes. And that's what we strive to achieve. And that's also called decentralization. And that's also, I think, the main reason that makes our Ava Labs very different from other crypto projects. Thank you.
Thank you very much. And next question is, in PBFT, when the number of the consensus group is increasing, the speed of the consensus is getting low. So how do you think you can resolve this issue?
Yeah, so I think that's a common question, because consensus is hard to improve. Why could we, magically solve the problem? As you may notice, we mentioned that we only sample the network by K. So we only ask a very small portion of the entire network. That means, unlike PBFT, which samples the entire network, you just simply ask all nodes and hope for 2f+1 responses. In our case, we're asking K and just audit the majority out of this K member. For example, if you have 2,000 nodes, probably you only have to ask 10. And you just, draw some partial conclusion based on this single sample. And of course, it is much weaker than asking the entire network, because what happens if you happen to sample some Byzantine nodes or adversary nodes, then bad thing could happen, right? So for each sample, we're actually relaxing the PBFT quorum to have a probabilistic, small size sample. And that way, we are trading off 100% safety guarantee for much better, scalability and more potentials for further trade-offs. So what we are losing here by, not following the paradigms of the line of PBFT-like work is that we think people are comfortable with probabilistic safety guarantee. And that makes sense because, even if you're a billionaire, the next day you wake up, when you walk outside of the street, you can still get hit by the car. No offense, but, still non-zero probability. And I don't think, having a much lower probability of safety failure sounds like a bad idea. I mean, if the failure probability is very low, lower than your hardware failure rate, then this thing doesn't matter. So we're making this kind of trade-off. Hope that makes sense to you as well.
Yeah, thank you very much. I believe it is helpful to understand. And next question is, according to the gossip protocol, when a certain amount of the network is under attack, isn't there any possibility for network to be altered?
You mean in our protocol or the? Sorry, could you repeat the question?
According to the gossip protocol,
Uh-huh.
a certain amount of network is under attack,
Uh-huh.
and isn't there any possibility for network to be altered, to be changed, to be altered?
Oh, that's a good question. So that's why designing such kind of protocol sounds easy, but it's actually really hard. So first of all, you don't want to ask a fixated like 8 neighbors because you don't trust those. K neighbors. You don't trust those K neighbors. And what you want to do is each time you have to reset. You have to randomize the choice of the people you're asking about, and then each time you're choosing different K people. If you repeat the process for enough amount of time, then math will tell you that you have already high enough safety guarantee. And in the case when the network is partially attacked, which could cause, so-called network partition, I guess. If you happen to sample some of them from the attack part, then what you will get, either the attacker just refuse to respond to a request, and they just hand there, no safety violation. But if the attacker just, responds you with the wrong answer, or, it just equivocates its response with arbitrary answer, then the question goes back to the first case I talked about. It's guarded by math. So either it refuses to communicate, in which, the system somehow gets stuck a little bit, but it can use timeouts. So you can always introduce some reasonable synchronicity assumption into the system. So to overcome this, for example, if this sample of K nodes don't get back to me in a short enough amount of time, then I can do another sample. Hope this answers the question.
Okay, thank you very much. And next question is, does new protocol need more 2/3 of good nodes still? And when a total number of nodes is less than 2,000, how high TPS and latency was shown?
Oh, so I think this is 2 questions, right? The first question is, sorry again, the first question.
Okay.
It went away.
Is the new protocol still need more 2/3 of good nodes?
Oh, I see. It depends. So I actually asked the same question like to our theory guy, like Kevin, and he said, it depends. and that's a very interesting thing if you think about it. So of course, you can tolerate slightly more than 1/3 of the Byzantine node in your network, but at the cost of losing liveness. So if you take a look at the paper, the white paper, you understand what it means. So you're basically trading off between, safety and liveness when the absolute, amount of adversarials in your network is huge. And the second question again?
Yes, second question is,
oh, I see. So 2,000 nodes and above, right? So I think I didn't do actually more than that, because the tendency already tells us, this thing, the throughput doesn't degrade as much as you may think, but I can somehow speculate. So think about the protocol. You only ask K people, and K, if it is a fixed constant, because it has to be fixed. It's actually a security-related constant. It's very weakly affected by n. So it barely grows, even when n grows to like as large as 1 million. Then I think in that case, there shouldn't be much degradation in throughput, because everyone is just asking k people, regardless of the network size. And there's no extra load introduced if your system scales up.
Okay. Thank you very much for sharing your knowledge. This was the last question, so thank you very much. You can return to your seats. 네, 좋은 말씀해주신 테드인 강사님께 다시 한번 큰 박수 부탁드립니다.